The thesis has been supervised by Ramon Costa and Gina, and in the jury we are three people: María Serra from the Universitat Politécnica de Catalunya, Samuel Zoboli from the Laboratoire d'Analyse et d'Architecture des Systèmes, LAS-CNRS, and myself from the University of Zaragoza. Mingrui, as you know, the act has three parts. The first part is the presentation of your thesis, the defense of your thesis, emphasizing the contributions of your work. In the second part, we will ask, the jury will ask. In first place, María Serra has the time. In the second place, Samuel Zoboli. And finally, myself will ask. When the three members of the jury have finished, I will ask again to Maria and Samuel if they want to ask some additional question. And I also ask the people, the PhD in the room or in the meeting, if they want to ask you something. Finally, the public act will finish, and we, the three members of the jury, we will join in a private meet just to evaluate and write your qualification. So it's my pleasure to introduce you. It's your turn. So go ahead.
Okay, I can start, right? Good afternoon, everyone. My name is Mingrui Chen. Thank you for attending my PhD defense. Today, I will talk about the state of charge estimation for metal hydride storage tanks. My supervisors are Dr. Ramon Costa and Dr. Gina. Let's begin with background and motivation. The global energy is undergoing a major transition from traditional energy to renewable energy. However, one of the shortages of the renewable energy is intermittency. For example, solar energy depends on sunlight, which is highly variable and cannot be controlled. To address the intermittency, we need robust and scalable energy storage systems. Among various energy storage technologies, hydrogen storage is emerging as a promising alternative due to the high energy density. In general, hydrogen can be stored in three ways: compressed gas, liquid hydrogen, and solid state storage. Both of compressed gas and liquid hydrogen have energy losses. So in my work, I mainly focus on solid state storage, which provides high hydrogen density at moderate temperature and pressure, and it provides large capacity storage. This is a schematic of a metal hydride tank, or we call it NH tank. In the charging process, the hydrogen enters the tank from the outlet and then reacts with metal alloy to form metal hydride and release heat. To quantitatively describe the reaction, we always use the pressure, compensation, temperature curve. The PCD curve is a very important curve, which shows the relationship between equilibrium pressure and hydrogen amount. The PCD curve contains two curves and three regions. Let's see the red curve first. In these two absorption regions, both pressure and hydrogen amount increase, while in this equilibrium region, pressure almost does not change, while the hydrogen amount still increases. Similarly, the desorption curve also has these three parts. Despite the potential, the state of charge or SOC estimation of the NH tank is still a key challenge. Specifically, only tank pressure, temperature, and flow rate are measurable, and the mapping between measurable variables and the SOC is very complex. And the absorption and the dissolution processes exhibit heterogeneous. It can be seen clearly in the PZ curve. Here, there is heterogeneous. Therefore, my thesis aims to design a SOC estimation framework for NH tanks. To achieve this goal, I developed and calibrate the NH tank model. Then I design nonlinear observers for monitoring the states of the NH tank. Then we can, based on the observer results, to estimate the SOC. Finally, I verify the proposed algorithm in experimental setup. This is the technical roadmap of my thesis. Part 1 mainly focuses on NH tank model and calibration. Part 2 mainly focuses on observer design and SOC estimation framework. Now I will introduce system modeling. Let's consider the mass transfer first. For hydrogen, the change in density can be described by this equation. Here, N is hydrogen mass flow rate into the tank, and here Nr is hydrogen mass flow rate absorbed by metal alloy. So this part is mass changes, and this part is gas volume. Then, if we by normalizing use the volume of the NH, we can get this whole mass balance equation for hydrogen. Similarly, for the NH, this part is volume. It's the volume of the NH. Then we can get this mass balance equation for the NH. In this model, the reaction kinetics Fr cannot be measured. So here we use commonly adopted empirical formula. Fr is piecewise function, and when the pressure P between the equilibrium pressure PQA and PQD, then Fr is 0. In equilibrium pressure, PQA and PQD cannot be measured too. So here we use Van der Waals equation to describe it like this. Next, we consider the heat transfer. The heat variation inside of the tank can mainly comes from two parts. One is heat transfer between the tank and the external environment, and another one is reaction heat. Then we can get these two energy balance equations for hydrogen and the NH respectively. If we assume that the hydrogen gas and the NH satisfy local thermal equilibrium, we can combine these two equations and get this simplified energy balance equation. Okay, so now with previous physical models, we can build this 3D state space model. And here in this model, the temperature can be measured by thermocouples. So this model can be reduced to a 2D state space model. In these two models, mass flow rate F in is one of the inputs. That means what we can control is mass flow rate. However, in many practical situations, what we can actually control is pipe pressure. So these two models are not suitable. To solve this match, we introduce a proportional pipe model. Here, this part is pressure difference between the pipe and the tank. Kp is proportionality coefficient. And then with this additional model, we can get a modified state space model. In this model, we can see here the pipe pressure becomes the input and the mass flow rate F in becomes output. This is the simulation of 3D state space model, and this is a charging process. This figure is discharging process, and here the first figure shows evolution of flow rate. We set a fixed flow rate, and when the pressure achieves the reference pressure, then we set a flow rate as 0. Since the reaction can release heat, so here as we can see, the temperature increases gradually and achieves to an equilibrium state, and then temperature decreases. Here is a figure of the SOC. As we can see in this equilibrium region, pressure almost does not change while the SOC still increases. Next, I will introduce experimental setup we used. This is a diagram of experimental setup, and the main components include the energy tank, several mass flow meter, several pressure sensors, and several thermocouples. Next, I will introduce the model identifiability and sensitivity analysis. In the energy tank models, there exists some unknown parameters. So we may ask if it is possible to uniquely determine these unknown parameters from the measured inputs and outputs. This issue is known as identifiability analysis problem. In general, we consider the following nonlinear systems. Nonlinear system here, data is a constant parameter factor. To analyze identifiability, we use a method called a correlation method. First, we can compute the output sensitivity matrix S, which stores sensitivity information of the model outputs. The main idea of the correlation method is we studied the absolute correlation matrix C. In this matrix, each element is correlation between any two columns of matrix S, and if the correlation is larger than this value, then we think the corresponding parameters influence system outputs in a very similar way. That means it's difficult. It's very difficult to identify these parameters based on system outputs. Finally, based on matrix C, we can calculate the total correlation of each parameter like this. This index tells us how difficult it is the parameters can be identified based on the system outputs. In the EdgeTech model, to analyze identifiability, we design the following mixed charging and discharging profile, and here this table shows total correlation of each unknown parameters. And in this table, the parameter with higher total correlation is more difficult to identify. After tracking the identifiability, we assume that all unknown parameters can be identified. So now we may ask, can we use these values from literatures directly? Therefore, it is necessary to know which parameters have significant impact on the system dynamics. This issue is known as sensitivity analysis problem. To analyze sensitivity, we use a method called first-order trajectory sensitivity analysis. The sensitivity of a solution can be defined as this partial derivative, and the sensitivity of the derivative of the solution can be computed as the following equation. Here, this part is 0 because, as we know, the input is independent with parameter z. Then, if we define this part as sensitivity trajectory nano t, we can get this first order trajectory sensitivity function. If we solve this function, we can get the whole sensitivity trajectory of each parameter nano t. In addition, the original system can be approximated by the first order Taylor expansion. Then after several steps, we can get this each state evaluation caused by a single parameter evaluation. We take the maximum of this value as sensitivity index. Here, this index tells us which parameter has significant impact on the system states. The evolution of lambda for logic in charging process is shown in this figure, and we can see here these two parameters CD and ED have no influence for logic, because here you can see the trajectories are always 0. Then this table shows sensitivity index for each unknown parameter, and we can see from this table these four parameters have significant influence on knowledge because like this have a larger sensitivity index. And similarly, the evolution of lambda for noise in training process is shown in this figure, and the sensitivity for each unknown parameters is shown in this table. And similarly, we can see from this table, these 5 parameters have significant influence on noise because, as we can see, the value is very large. Next, I will introduce model calibration. Let's consider the 2D state space model. In this model, since Fi is a non-convex function, so in my work, I use particle swarm optimization method because it is suitable for non-convex problems, and GSO has fast convergence speed, and it only needs some simple implementation with few parameters. To evaluate the calibration quality, we use mean magnitude of relative error, NRE, as a projective function. Here, the first part is NRE of the flow rate, and this part is NRE of the pressure. And these two figures show the calibration results. This is a figure for pressure, and this is for flow rate. And as we can see from these two tables, the calibration results based on PSO method is very good. Next, we can see the calibration for 3D state space model. In this model, there are 2 outputs. So if we still use the single objective optimization method, it may result in the case where one output fits very well, but another output fits very badly. Therefore, in my case, we use a multi-objective optimization method. Similarly, we build 2 objective functions. Here, this one is NRE of the pressure, and this one is NRE of the temperature. Then we can plot this Pareto front based on Pareto search algorithm. I want to emphasize that each point on this Pareto front is a trade-off. It's a trade-off between the pressure accuracy and the temperature accuracy. So now the problem is, how can we choose a best one from these points? To solve this problem, in my case, I calculate the normalized Euclidean distance between any point and the ideal point, and then we choose the point with smallest Euclidean distance. Here in this figure, the green one is ideal point, and Here the red one is point we selected. These two figures shows calibration results based on multi-objective optimization method. This figure is for temperature, and this figure is for pressure. And from the results, we can see that the calibration results are good. Okay, now with previous analysis, we can start estimating the SOC. The SOC is defined as the percentage of the current hydrogen amount to the maximum hydrogen capacity. Here, maximum hydrogen capacity is known, and is known. But here, current hydrogen amount is unknown and cannot be measured. To estimate the SOC, a very simple method is to integrate the flow rate directly. However, this method requires the initial hydrogen mass in NH tanks. Here, this is the initial mass, and actually we don't know it, and it introduces cumulative errors in the flow method, and the error is introduced in this part. To estimate the SOC more accuracy, in my work, I use a better method, observer method. Let's consider the 2D state space model. From this model, we can note that this equation is satisfied. From here, if we product V of G at this side, then after several steps, we get expression for SOC. In this expression, both of these variables, VH, VG, is known, and only X1 and X2 is unknown. So we need to find a way to estimate X1 and X2. Then the SOC estimation problem can be transformed to an observer design problem. In general, we consider the following multi-input, multi-output system, and the objective of the state observer is to generate a signal X hat that converge to the two system trajectories asymptotically. Before designing the observer, a key point is to analyze the observability of the model. That is, it is necessary to analyze if it is possible to reconstruct the state variable X from the measured variables and the model output. This figure shows observability property. Let's see this figure. In this case, different system state trajectories generate the same output. So this system is non-observable. in this case, different system state trajectories generate different output. So in this case, the system is instantaneously observable. Instantaneous observability can be tested through the Jacobian matrix rank of the observability map. Here, observability map consists of system outputs and its derivative. If the Jacobian matrix of this observability map is full rank, then we say that the system is locally instantaneous observable. In the abstract model we built, we consider the third order observability map for the 2D state space model, this, and its Jacobian matrix takes the following form. In this matrix, distance is not zero. So if we want to analyze the rank of this matrix, we should analyze the sign of star 2. Let's consider the case where Fi is 0, and in this case, from this part, we can see star 2 is 0. So in this case, in the case where Fi is not 0, this matrix is not full rank. Then the system is not instantaneous observable. Next, we consider the case where Fr is not 0. In this case, we use numerical analysis method. That is, we plot the values of this term in this figure, and from this figure, we can have a conclusion that when the system when Fi is 0, the system is not observable. And when Fr is not 0, the system is observable. Although we have this conclusion, we still don't know when the system enters the observable region, because as we discussed before, Fr is unknown and cannot be measured. So we need to find a way to estimate Fr. To achieve this goal, to solve this problem, we use the following subsystem, and it's very easy to design the following differentiator for this system. However, this differentiator is very sensitive to measurement noise, because here we use the derivative directly. To avoid using derivative, in my work, I use unknown system dynamic estimate, USD. The main idea of the USD is to impose the low-pass filter into both input and measurable fiber. Then we can design the following manifold fiber, and when the filter parameter kappa goes to 0 and the time goes to infinite, this equation is always satisfying. Then based on based on this invariant manifold, we can design this estimator for alpha. Now with previous preparations, we can design the following Lumberg-like observer for log G. Here, this part is a copy of the original system, and this part is feedback term. Here, L1 is a tunable constant observer gain. For this observer, we have this theorem, and this theorem means that the observer error x1 tilde exponentially converges to a small compact set as time goes to infinite. To estimate loss, we should consider the following subsystem, and when the system is in observable regions, that is when the system is in region omega 1 and omega 3. Fr is a function with respect to x2. So based on inverse function theorem, there must exists the following functions. Considering this, we can design the following Lumberg-like observer for OS. If you look at these two observers, you will find here we have additional term, and here SFR is the time varying switching function. When the system is in observable region, SFR is 1, and when the system is in non-observable regions, then SFR is 0. The choice of SFR is based on the estimation. It's based on the estimation of FR, and here the estimation of R is from USD, and it's numerical value. So it may not exactly 0. So here we design a tunable tolerance. This is a figure the evolution of the estimation error is shown in this figure, and when the system is in observable region, that is when SFR is 1, the estimation error decreases exponentially, and when the system is in non-observable region, that is when SFR is 0, the estimation error is frozen. Finally, we have this theorem, and this theorem means that the estimation error x2 tilde exponentially converge to a small compact set if the system stays in observable regions for a sufficiently long time. To verify the efficiency of the proposed observer, we conduct a simulation, and this figure is evolution of mass flow rate FR, and as we can see, it converges very fast. And this is a figure of observer X2 hat. We can see here in this region, the observer is not converged because in this region the system is in non-observable region. This figure is SOC estimation, and we can see this SOC estimation has same trend as observer X2 hat. These two figures show the experimental results, and this is results of observer X2 hat, and this is as for the SOC, and we from these two figures we can see that the proposed observer is also useful in practice. Next, I will introduce the SOC estimation with differential detectability based observer. Let's consider this 2D data space model. From now, we already designed a lookalike observer for this model. However, the above observer requires inversion of the expression for FR, and it requires substantial offline data for training. So we may ask, do we have a better method? To answer this problem, we consider the following nonlinear system in which the output map is linear. I will introduce some concepts about this system. The first one is the differential detectability. We say that a system is differential detectable if there exists constant positive matrix P and some constants such that the following inequality is satisfied. This property means that different system state trajectories generate the same output. However, these two state trajectories converge to each other asymptotically. The second is the non-expansiveness. And we see that a system is non-expansive if there exists a constant positive matrix P such that the following inequality is satisfied. This property means that the distance between any two state trajectories would not increase. The third one is contraction. We say that a system is uniformly contracting if there exists some constant such that any two state trajectories converge to each other exponentially. Since the original system, since the output of the system is not linear, so in my work we introduce the following transformation that linearizes the output. Then the original intent model can be rewritten as following switching system. Here sigma is switching signal which corresponding to the following three cases. Similarly, before designing observer, we should analyze differential detailability. For the case where Fi is 0, we can see this equation is satisfied. Then we can see this inequality is satisfied based on the definition of non-expansiveness. We can see that the system is non-expansive in this case. For the case where FR is non-zero, we use a numerical analysis. That is, we can choose appropriate constants mu and q. Then we design matrix P to make the following inequalities satisfied. In some laws, the system is non-expansive if Fi is 0, and the system is differential detectable when Fr is not 0. So now, based on the property of differential detectability, we can design the following switching observer, and the observer dynamics are switched based on the signal sigma. For this switching observer, we have this lemma, and this lemma means that if the system and the observer stay in the same observable regions, the distance between the x scatter t and xt would decreases exponentially. If the system and the observer stays in non-observable region, the distance between x scatter t and xt would not increases. This is switching mechanism, and here the observer dynamics are switched based on the estimation of Fr, and here this value is from this value is from USD we designed before. Finally, we have this theorem, and this theorem means that if the system stays in observable regions for a sufficiently long time, the switched observer is uniformly contracting, and the observer error decreases exponentially. To verify the efficiency of the proposed observer, we conduct this simulation, and here this is the evolution of Fr, and the estimation of Fr is from USD, and as we can see, it converges very quickly. Similarly, the observer is too head. It's not converged in this region because in this region the system is in non-observable region, so we cannot design observer for the rest. This is estimation. This is estimation of SOC, and you can see it has the same trade-off as observer S2. This is experimental results of the proposed observer, and from these two figures, we can see the efficiency of the proposed observer in practice. Here is the SOC estimation. Next, I will introduce SOC estimation with high gain switched observer. From now, we already have two observers. However, the above two observers have a significant non-observable region. That is when Fi is 0, the system is non-observable. So we may ask, how can we reduce this region? To solve this problem, we have to consider the complex 3D state space model. Similarly, we should analyze the observability of the 3D model, and we consider the third order observability map for 3D state space model. And for the case where Fi is 0, we get this Jacobian matrix, and we get this four very complex expression. Fortunately, we after analyzing only when the tank temperature X3 is equal to the ambient temperature. This matrix is the rank of this matrix is not full rank. Then the system is not observable in this case. For the case where F up is not 0, we consider the following submatrix of Jacobian matrix. Fortunately, in above slide, we already analyzed the rank of this matrix. That is, the system is observable when Fi is not 0. Therefore, we have this conclusion, and only when Fi is 0 and tank temperature X3 is equal to the ambient temperature, the system is non-observable. And in other cases, the system is observable. The original NH-tank model can be rewritten as following: input a fine nonlinear switched system. Here, sigma is a switching signal which corresponding to the following four cases. We assume that there exists a function defined as system output and its derivative. Then we can transform the original system to a new coordinate. That is, the system dynamics in eta coordinate can be rewritten as following triangular form. For this triangular form, we can design high-gain observer in eta coordinate. And if we back to the original x coordinate, we can design the following. We can design this switching observer. Similarly, we have we have this additional term SFR, and when the system is in observable region, SFR is 1, and when the system is in non-observable region, SFR is 0. And SFR is switched based on the estimation of FR and the estimation of temperature, X3 hat. The main idea of the observer is that first we transform the system into a new coordinate, eta coordinate, by using this definite reason 5, and then in this eta coordinate, the system is triangular form. So we can design a Hygiene observer for this triangular form, and then we back to the original coordinate by using the inverse of this definite reason. This is a switching mechanism we designed. Here the observer dynamics are switched based on the estimation of FR and estimation of temperature X3 hat. Therefore, we have this lemma, and this lemma means that if the system this lemma means that in each observable region, the estimation error decreases exponentially. Finally, we have this theorem, and this theorem means that in whole process, if the system stays in observable regions for sufficiently long time, the observer estimation error can decreases exponentially. Similarly to verify the efficiency of the proposed observer, we conduct this simulation, and here the estimation of FI is from USD. I want to emphasize that let's look at this observer X2 hat, different from the observer. The above observer we designed up here, even though the different from the above observer, almost each regions are observable. So here we can see the estimation, the observer X2 hat converges at the beginning. This is SOC estimation, and we can see it converges very fast. These four figures shows these 4 figures show the experimental results, and this one is the estimation of SOC. We can see the estimation result is more or less good. Next, I will have a conclusion and propose some problems can be solved in future. The main contributions of my thesis can be divided into 3 parts. The first is about the H-type model. I developed physical and state space models. Then I analyze system behavior and charging, discharging, and mixing conditions. The second is about the parameter analysis and calibration. I analyze the identifiability and the sensitivity of the H tank, and then based on these results, I calibrate the H tank model using PSO-based single objective and multi-objective optimization method. The third is about the SOC estimation framework. I design a USD to estimate the absorption rate FR. Then I design three observers for monitoring the states of the H tank, and then based on the observer results, estimate the SOC. The following open issues could be addressed in future work. It is interesting to investigate SOC estimation using only pressure and temperature sensors because the price of the mass flow rate is very expensive. It is interesting to develop adaptive nonlinear observers because in the status space of the H tank there exists unknown model parameters. It is interesting to address the local thermal equilibrium assumption by integrating a thermal gradient model for large scale H tanks. In my PhD study, I published 4 journal papers and 4 conference papers. At least here. The final is the acknowledgement. My thesis was supported by China Scholarship Council, and the thesis was supported by the following project. Thank you for your attention. Any questions?
Can you hear me, Mingrui?
Yes.
Mingrui, can you hear me?
Yes.
Yes.
Okay, that's perfect. We are going to start the second part of the act, just the turn of questions. We are going to start with Maria Serra. So Maria, it's your turn, please.
Okay.
Okay, thank you for your presentation. Congratulations. I like the thesis very much and the presentation as well. But I wanted to ask you some questions.
Okay.
Okay, about the model, I have one question that I think is in slide 11.
Yes.
Yes, I doubt why the last term in the first equation, this change of molecular energy,
Yes.
is not the same as the yes, as this one. Why they are? Or if you can explain these hits, what are?
Actually, in our case, because the gas and the DH satisfy local thermal equilibrium. Here, this is satisfied, so we don't consider this part. And this one is I mean because the gas is absorbed by metabolite. So when the hydrogen gas enter the edge, we only need to consider the temperature of the solid. This is the change of molecular energy between the gas and between the gas and the solid. I mean because the reaction is that the hydrogen enters the solid. So here we need to consider the temperature of consider the temperature of gas. Is specific heat of gas.
Because
This part considers the reaction heat between the gas and the metaboloid.
yes.
So here we should use two temperature.
Okay.
And when the gas enter to the solid,
Yes.
the temperature of gas is equal to the solid. So here, actually you can write here TG is also key. Yeah.
Okay.
And
I understand.
And since local thermal equilibrium is satisfied, then as you can see in this simplified we don't consider
Yeah, yes. This I understand, but I understand the second. Okay. Okay, thank you. Then yes, in the thesis in page 25, I don't know if you have.
yeah, sure. Is on
Page. Yes, probably. Because here you say that you remove the thermal dynamics, or you remove the thermal part of the model to go
yeah.
from the
cross 3D
yes to
to
2D.
2D, yes.
Yes, and you say that the heat exchange is neglected.
Yeah.
With the exterior part.
Yes.
I don't agree because, or in any case, you don't consider, but you don't assume that this heat exchange is zero. I understand.
Yeah, I agree with you. I mean, here the 2D in this 2D status space model, because the temperature can be measured by thermocouples. So if I can show you the 2D. Yeah, this is a 3D model, and this part is temperature because this part can be measured by some colors, so we can think the temperature is known. So we can simplify this status space model to 2D model.
But in figure 2.5, I think that figure 2.5 is from the 2D model.
From 2.5.
2.5.
Okay.
Yes.
Okay.
This is a figure from the 2D model,
Yes.
but then the temperature here,
Yes.
because you don't have any real system to also. So how have you created the curve here in temperature?
Actually, this temperature is a real data because here our temperature is from thermocouples. We put thermocouples outside of the tanker. So we this is this
Okay.
actually this is experimental data we
Okay.
collect.
Okay, I didn't
Yeah.
understand this.
Yeah. This is not from the this temperature is not from the expression of temperature, very complex. Trend.
Okay. Then I think that you have assumed in your thesis
Yes,
that
yes.
you don't put any refrigeration, any thing to control the temperature in the metal hydrate system.
Yeah, actually, I can show you the experimental setup. Okay. Here you can see this is the DNH tank, and DNH tank is placed in experimental environment. So actually, in the laboratories, they design the researchers design cooling system to control the temperature. But in our case, we didn't consider the temperature control system.
Because
And yeah.
this maybe could change a little bit your results, do you think, or not? Because if, for instance, if you maintain it, because I think that normally in metal hydrates, when they charge or discharge, it is interesting to maintain the temperature quite constant in order that you can charge and discharge faster. Is this right?
Yeah, it's right. I agree with you.
Okay.
Yeah, it's right.
Then, if you don't have this cooling or this heating, first, maybe this changes the velocity that you can charge or discharge.
Yeah.
And then the other comment is that if you would put this control temperature to maintain it quite constant, this would change your results in the observers, especially the third one, that you consider temperature as an output that gives you information.
You mean the temperature? The temperature with the influence.
I mean, if you operate maintaining the temperature constant, and temperature is always constant in your operation because you maintain it with a controller, then your observers would have the same performance. The third one in what you have temperature as a measure.
In the third observer, I designed only when the tanker temperature is equal to the ambient temperature, it's not observable. So as you said, if the temperature is maintained constant, and unfortunately, it makes the system in the non-observable region. The third observer cannot work.
So you only need that the temperature is not the ambient temperature, but you don't need that they change, that the temperature change with time. This is not necessary. for the observation.
Yes, I think if the temperature is not equal to the ambient temperature, the ozone can also work, can still work.
Okay.
I think.
Okay. Thank you.
Thank you.
One little comment about that, maybe saying 3D and 2D, calling 3D models or 2D models
Yeah.
is a little bit confusing because I sometimes 3D and 2D is used to say that the amount of dimensions that physically uses your model is representing, and not the amount of states. This may be
Okay. They could work on.
yes. In the thesis, you say that in page 46, but maybe it's not necessary to go there. That it is not necessary to repeat the identifiability analysis for the 2D model because you already did the identifiability analysis for the 3D model.
Yeah.
And then you say, no, it is not necessary to repeat it. But in the 2D model, you have one less output.
Yes.
And this is not important.
It's important. It's important, but in my thesis, I analyze identifiability of 3D model and and the results shows that all unknown parameters can be identified. That means each unknown parameter influence system outputs in different ways. The 2D model is derived from 3D model through dimensional simplification, and this simplification does not change the way that the parameter influence system output. So in 2D model we don't analyze identifiability because the unknown parameter in the 2D model influence system outputs are also different. And yes.
But if you have an output, one less output, then you can identify as well all the parameters.
Yeah, because in 3D model, in 3D model we have 2 outputs, and we can identify all unknown parameters in the Einstein model based on these 2 outputs. And okay, if we don't consider this part, if we don't consider the temperature, this pressure, this output pressure, in this part, the unknown parameters influence the system output P in different ways. So here, if in this simplified model, the unknown parameters in this part influence pressure. Also is different. So we can identify the unknown parameters from this pressure. That's what I think.
Okay. Then, okay, the sensitivity analysis
Yes.
is used in the calibration, or the results of the sensitivity analysis are important for the calibration, and you have used them.
Yes.
In what way?
In sensitivity analysis, we can judge which parameter has a significant impact on the system state, and because in that research researchers already have some values of these unknown parameters. So therefore for those parameters with higher sensitivity index, we couldn't use the values from that research. And when we calibrate the Einstein model, we should calibrate the parameters with higher sensitivity index. And for those parameters with lower sensitivity index, we can use if the accuracy of the system is not important, we can use the values from that research directly. So this will simplify the calibration process and reduce some computation costs.
So basically, what you say is that you selected the parameters that should be identified according to the sensitivity analysis, and the ones were identified, and the other ones you took the data from the literature.
Yes. Okay. Because if we use values from that research, we decrease number of parameters that should be identified.
Yes.
Yeah, and it will decrease computation cost, I think.
Okay.
Thank you.
Yes, for instance, in page 131 of the thesis,
Oh,
130.
not just.
Yes, I think maybe a little, or this one, or below. Yeah, this one. This one. Yes.
Okay.
Here, the estimation of the state of charge is much slower, no, than in the other examples. You needed more time.
Yeah.
This is real validation, experimental validation.
Yes.
One question is if you know why, and the other one is if you have done, because in the simulations it didn't seem that this had to be so slow, but
this is simulation, and
yes. Yeah. So you know why in the experimental validation you need this amount of time for the reduction of the error.
Actually, I think because in this chapter, I designed the observer that is based on the differential detectability, the problem is this property is a global property, and what we can guarantee is that what we can guarantee is that the observer converge to the two system states asymptotically, but we cannot control the convergence speed. We cannot control the speed. So in the simulation, although it's
Very fast?
yeah, also it's very fast, but in experimental data, we cannot control the convergence speed.
But you don't know the reason why
Yeah,
this
yeah.
happens. This
Mm-hmm.
difference between simulation and reality.
Yeah. I think maybe the reason is as I said because we cannot control the convergence speed, and it's already the best solution.
Okay.
You,
Okay, and only two more questions about the experimental or general. About the experimental work, have you participated in the experiments and in the acquisition of the data and even in the design of the experiments?
Yeah. Actually, okay, I want to experiment it out. Yeah, this is experimental setup, and at first, at the beginning of my study, this setup is completed. But what we can control is pipe pressure. For instance, we can control the pressure. We can control the pressure control and to control the pipe pressure. But the problem is in many laboratories, what they control is fluid. So I collaborated with Brian, and we designed this setup, and the final version of the setup, we can control both pipe pressure and flow rate. And for experiment, I collect the experimental data with Brian, and we did charging and discharging experiment, and we collect the data and analyze the results. Yeah, thank you.
Okay, thank you. And only one last question.
Yeah.
Is if you have thought if these same observers that you have designed
Yes.
can be applied to other systems that are not metal hydrides, but that are similar or have similar properties.
The observer design can use for another model. Here, as you can see here, in this chapter, I designed general lumbar-like observer, and for another model, if you have a system model, you can use this lumbar-like observer. First, you copy from original system, and here you can put feedback feedback term. It's driven by the estimation error. So I think this is more like an observer can use for another model. Here and in this chapter, I design the observer based on differential detectability property. And if we before we use this observer, we should linearize output for those output. It's not a linear. It's not a linear. We cannot use this observer. Yeah, and here in this chapter. In this chapter, I design high-gain observer. This high-gain observer is for the system with the following triangular form. So, if we want to use this high-gain observer for another system, we should first transform the system into this triangular form. Then we can design high-gain observer for this and back to the original coordinate.
Okay, thank you very much.
Thank you.
Okay, Maria, thank you very much for your question and for contributions to the work of Mingrui. Samuel, it's your turn.
Okay, thank you. Thank you very much for the presentation, for the thesis. I mean, it was very, very nice reading it. Especially, I really appreciated the fact that coming from more of a theoretical side, I see someone that actually applies control and observation. In real life, it's very, very nice to see. So I have some questions.
Yeah.
First, related a little bit to the identification and calibration part, and then a little bit more to the observer part.
Okay.
So my first question is related actually to the identifiability sensitivity analysis that you do, because from the method that you use, from my understanding at least, you basically collect some samples of the output.
Yes,
to get the sensitivity matrix and the correlation.
Yes, get this machine.
Yeah, exactly. So, my question is, I mean, I guess this output is generated by some inputs that you inject into the system.
Yes.
How did you choose this input so that you have like a matrix that actually represents the good behavior of your system? Like, do you have some, I don't know if you know, persistence of excitation type of properties of your input to be sure that what you get is actually representative?
Yeah. If I don't know, you're asking how to choose the input?
Yeah, to get, let's say, good samples for your computation of the sensitivity matrix.
Yes. I think we what we can choose is the sampling time of the output. We should choose a bigger sampling time of the output, because if the sampling time of the output time is, these metrics will, I mean, the law of these metrics will very strong, has a strong correlation. And first is choose the bigger sampling time, and for the output, because this identifiability is for 3D model, we have two outputs. So in our case, we choose those outputs, and then we correlate this partial derivative for all the unknown parameters, because we know in the Einstein model we know which parameters is unknown, so we analyze all the output for all other campuses. Yeah.
Okay. So already you explained me something, the importance of the sampling time. But my question is actually related to how you generated those outputs.
Output, you can, because you can in the simulation you can
Okay, simulation.
Yeah, in simulation you can perform the simulation in the MATLAB, and you can get you can import export the simulation data from to the workspace, and then you can.
Okay, just literally like what you gave to the system to get those outputs. What I guess it's more or less. I understand.
Because you can get the whole trajectory from on this differential partial derivative in simulation, and you can.
Yeah, but like the initial condition, how do you choose the initial condition? How do you give the input to the system so that it generates that trajectory that you selected? Like, do you have a particular, like, I don't know, pseudo-binary sequences or sinusoidals to generate those ones, or it's just any output?
Yeah. We select all the outputs, the data of all outputs, and build these meshes.
Okay. So still related a little bit to the identification problem and the calibration. You use PSO.
Yes, PSO.
Yeah. That you say that's fast convergence speed. Is this like a formal guarantee, or is just like experimental? Because from my understanding, at least PSO, you basically take some points at random with some velocities and then you explore.
Yeah.
So I guess that asymptotically, in some sense, you have like some probabilistic guarantees of converging to the global optimum.
Yeah.
But in practice, is this true? Or like maybe some gradient descent algorithm with a smooth version of the objective, because your objective function is not smooth, already reduced. They've been similarly good.
Yeah. Actually, in your case, Fi is a non-smooth function, and it consists of piecewise defined parameter, and shows strong nonlinear behavior, especially in sorption rate Fi and equilibrium pressure PQ. As you said, actually we can use the gradient method, but the problem is in our objective function we have piecewise definiter, and the derivative or derivative may not be continuous and not well defined in some regions. And when system dynamics switch, when system dynamics switch, the derivative may not continuous. So the derivative information is not reliable. We think. However, the PSO method does not depend on the derivative information, and it is much robust for the non-smooth, and it is much more robust when dealing with the type of non-smooth landscape. So in our case, we use PSO method. Actually, we in my work, we also try to use another algorithm such as genetic algorithm and anti-colony algorithm, but in our experimental case, PSO is more has more faster scale. So we give up genetic.
Okay, thanks. And do you think that this method could be, in some sense, profitably extended to other type of tanks and experimental setups, given that I guess
Yes.
it's a little bit like computationally expensive. So if you have a small model with not too many parameters, maybe it's effective because you can explore the space pretty efficiently.
Yes. Yes. Actually, I think the PSO can extend to another model, but in our case, we only use PSO for the specific hashtag calibration problem. Yeah, I think this message. But actually, in researchers, in general, the hashtag models are always 2 or 3 dimensional models, and for higher dimensional models, PSO can be used, but it maybe needs longer computation methods. Thank you.
Okay, the last question on this part, and then I move to the observers. Just one question first. You show some plots of curve fitting for your trained model to the data.
Yes.
I just wonder. Okay, after we will go there. 1 second.
Oh, okay.
So the plots that you show is just one curve. I wonder if you did some like statistical analysis of the validity of your models. Like, did you try many runs and see if actually your model was fitting well over the whole test set? Like, do you have a train set on which you trained, and then a test set, and then you mesh you check if your model that you derived from the train set also generalizes to the test set or not?
I'm not clear. You mean why we don't?
It's still an identification problem.
Oh,
It's still the modeling problem.
okay.
So you obtain some parameters given from some data.
Yes.
And then you test your model.
Yes.
And you check how well it fits in new experiments, right?
Yes.
Okay. Did you try, like, just also out of curiosity, to see how well your model generalizes to different type of initial conditions or inputs, like, because what you show is simply one graph.
Yeah.
But maybe it would have been nice to see some average plots, some like standard variation of the errors.
Yes. Actually, you mean the sensitivity analysis and identity analysis is local. So
okay.
Yeah, it's local. It's local based to verify the calibrated model and different operating conditions. We choose charging, discharging, and mixing processes, and the sensitivity and the final sensitivity and final sensitivity results can be get by considering all these processes, and in charging and discharging, we use different initial values, and in my thesis I give the results.
Maybe I lost them.
Here. This is we use different experimental data, and here is the calibration results for FR, and This is for pressure. It's not very well, but generally it can generate.
Thanks a lot. Okay, you can move to the observers. So I would like to start from the Wimberger type.
Okay.
So, looking if I can find the page that okay, the slide 36, actually the one before. So yeah, okay. First, I would like to understand a little bit better why you use the USDE for YouTube.
For YouTube, because
Isn't it measurable? It's an input, right?
yeah, YouTube is measurable. So we can impose a low pass filter on the YouTube signal, and
But I
because
mean, do you need the derivative of YouTube? That's
no, we don't use the derivative. I mean, in this version, U2F is the low pass filter version of the YouTube.
yeah. My question is, why can't you just use U2 directly in your computation there of FR? This that I'm not understanding directly.
This one?
Yeah. Why can't
Because,
they just use U2 instead of the filtered one?
because we only consider these sub-matrices, and here we only have the YouTube. Okay, I want to show you. Yeah, this is a 2D model, and if we want to estimate FR, we can only use this one. We need to consider this.
Yeah.
And so for this subsystem, we impose low pass filter on YouTube and X1. Then we can design this manifold variable, and when the power goes to 0, t goes to infinite, this is satisfied. So this is equals to 0, and then if we move this part and at the right side, so we can get this.
This I agree. But
Yeah.
like, my question is, why can't you using the manifold variable directly U2 instead of U2F? Maybe I'm missing something. But this is basically the idea.
Sorry.
You see, in M, the manifold variable, you have U2F. Yes.
U2F.
Yes. Why you can't you use U2 instead of U2F? Why do we need the filtered variable there?
Yeah, because compared with U2, the filtered version U2F is more smooth, and
Okay.
it can deal with sensitivity to the measurement noise.
U2, the measure of U2 is very noisy.
U2 is mass flow rate FE, and we measure the mass flow rate FE by mass flow meter. So in experiment, I think it truly has measurement noise.
Okay. And then related to the dilemma, I'm not sure I agree on the last sentence. In the sense that, sure, you can prove that if k goes to 0,
Yes.
then the manifold variable goes to 0.
Yes.
But then how can this prove that the set where you did m is equal to 0 is invariant for k positive?
I want to show you in series, and
because I read the proof and I agree up to
Yeah.
almost up to almost the last line. And the last line I don't understand.
Here, this is
This is
this is one of m and so on, and when if the kappa goes to 0, this this value is bounded by
I agree.
kappa lambda,
Yeah.
and it's bounded by kappa lambda. This is satisfied.
Yes.
So when the kappa goes to 0, so goes to 0, this is bounded by 0.
Yeah.
But it must be positive. So this is satisfied. It cannot be negative.
Yeah, sure.
Yeah. So this is satisfied.
Sure.
So,
Then is last. There's the last sentence of the theorem that says then that limit implies that the manifold is invariant for k positive. So I agree with the statement that if I take the limit, the compact set where I converge is shrinking to 0.
Yes.
But then if kappa is positive,
Kappa is positive. Yeah.
in the last sentence you select kappa positive.
Yeah. If kappa is positive, actually it's a bonus. It's a bonus, and
Okay. So
But-
the
but-
manifold is not invariant.
but we can design. We assume that the kappa is very small. It's very small enough. Yeah. So when kappa goes to 0, I think that this limitation is
So your statement is I stay sufficiently close to that
close to the 0.
to 0.
Yeah.
Okay.
And actually, the condition that this equation is satisfied, that is that the kappa we design smaller, a small enough kappa, then this is satisfied.
And how do you choose the kappa small enough? Because I guess that if you choose kappa small enough, you increase the sensitivity to noise.
The faculty signal and the true signal has phase delay, and to reduce the phase delay between the faculty version and the true system, we should decrease the filter parameter kappa. However, a small kappa is very sensitive to the measurement noise. So we should choose kappa based on the experimental data we calculated. Actually, it's a trade-off between the robust and phase.
Okay. So you select it through experiments. You do some experiments with different kappas and you select the one that you prefer.
Yes.
Okay.
Yes.
Okay. Thanks. So can you go to slide 40?
Slide 40. This one?
Is it 40? Oh, no, maybe 41.
41.
Sorry. Sorry. Next one? No, 42, sorry. Go at the beginning of the contraction based. Next one. Yes, okay. So here you say that the Bloomberger observer requires substantial offline data for training.
Yeah.
Where do you have to train the observer?
Here, around to Bloomberger. Here,
Okay.
In this Bloomberg observer, we use X bar, and but actually we can use this in this part we can calibrate the data in the simulation with different X2 u1 and y, and we get the data of fr. We can design, we can train the neural network to inference to calculate this set. This Taiwan is actually a neural network we train.
Okay.
So here we train two neural networks.
Okay. So it's basically an open loop prediction.
Yeah. This neural network is trained offline. Trained offline. Yeah.
Like when you deploy it online, X2 is estimated in open loop. There's no feedback.
Yes. This X2 bias is open.
And do you think there could be more robust methods to estimate X2 than this one?
Yeah, so that's why we designed this differential detectability based on.
Okay, so
Yeah, and here.
The idea of the differential detectability based one is to remove the dependence of the neural network.
Yeah. In this differential detector based observer, we needn't train the neural network based on the experimental data.
Okay.
Yeah.
Thanks.
Thank you.
Thanks. Sorry, I don't know how much time I have. I try to be fast and reduce my questions. I have.
Don't worry. You can ask as much as you want.
Okay. But also for him, I guess. So there's a point. I really like this part on differential detectability because it's more in control. I have a question about what you say in your thesis. I don't remember exactly the point.
Oh, okay.
But the point you say that differential detectability is less stringent than local instantaneous observability.
Yes.
Now, my question is, do you think that this is, I mean, I have an idea, but I want to know what you think about this. That this is still true whenever you define differential detectability with a constant metric. So when you have an Euclidean metric,
you need this metric.
yes,
yeah.
Because here you're asking something a little stronger than classical differential detectability. Here you're asking the condition to be verified with a constant p.
Yeah.
So, do you think there could be cases where your system does not verify that condition over there, but it is locally instantaneously observable?
It's a local property. I mean, so.
My question is: when I agree with your statement that detectability is less stringent than observability, but here you're asking something more.
Yes.
Here you're asking detectability with a constant metric. So I am not sure. I mean, at least I don't know if this is true, that this condition with constant p is less stringent than observability.
Actually, if T is constant metrics, it's considered the Euclidean distance between the two state trajectories, and if this P is not constant, it's in the Riemannian form. So I've read some papers about Riemannian form, and this will be considered in the future.
Okay. So, what would be like just your guess? Do you think that I could have, for example, a system that is locally instantaneously observable, but it's not differentially detectable with a constant speed? That's my question actually. Because in your thesis you say that this is stringent. So in some sense I would expect.
No. I in the thesis I I write the observability is more stronger
Yes.
than this. Yeah. And because actually the observability property requires different state trajectories generated different output. But this property we only need the system trajectories are continuous, and it's just for. In this case, it's non-observable system. But so if we want to design observer based on observability property, we cannot design observer. But if we use this property, we can design observer for.
Okay, thanks. Okay, I also have a couple of questions, and then just some general ones. If you just, I really like the fact that you study the switching problem, sort of access to desynchronization in switching. However, when you have switching systems, there may be some issues of having some form of, I don't know if you can call it like Zeno behavior, where you have basically infinite many switches in finite amount of time.
Yeah.
So my question is, and I do not have an answer for this. I would like to know what you think about it. Do you think it's possible for a system to satisfy your condition that you have over there, but have many fast switches in between observable and non-observable mode? Why do I say this? Just to let you know, because if this is possible, and in the non-observable region, you don't have a perfect non-expansion, you may have an overshoot.
Yes.
And if I switch too much in the wrong times, I could diverge, ideally.
Yeah, actually, it truly exists. Yeah. So, for the fast switch, what we can only guarantee is input to state.
Okay.
Yeah. This theory is for the smooth slow switch.
Okay, so you assume that you switch not too fast.
Yeah.
Okay.
Because here the observer dynamics are switched based on the estimation of FR, and the estimation of FR, you cannot guarantee this estimation is very close to the true FR. So when the observer switches, when the system switches, the desynchronization is still. Problem we need to deal with.
Thank you very much.
Thank you.
So last question is on the observer, which is on the infinite, the high gain.
Okay.
I found it pretty complicated assumptions that you need for the application of this approach. And the one coming from the paper from Brady and Associates.
Yeah.
So my question is, how verifiable is this assumption? I mean, did you compute yourself the diffeomorphism that changes you into the triangular form? And is it easy to find in this framework?
You mean this?
Yes.
Actually, because this is the observer for 3D model, and it only has 2 outputs. So I think it's very easy to build this technology. In my simulation and in experimental part, I write this technology, but in my thesis, I don't write the accurate.
So you found the function phi that transforms you into triangular form.
Yes.
And do you think this is generalizable to other types of tensor? Other models, not types, maybe.
I think if you can, because this method is for this input affine nonlinear system. So I think if you can for the system, if you can write the system model in this form, then you can transform the system to triangular form and design.
Okay. Thank you very much.
Thank you.
Okay, just a general question then.
Okay.
Between the 3 observers that you proposed, which one do you think would be the better fit for like practical application, like to bring out into the world, into the industry? Which one do you think? What are the advantages and the disadvantages of one, and which one would you pick?
Actually, the 2D model is suitable for the case where the heat transfer between the tanker and the external environment is not considered. However, the limitation of the 2D model is the large non-observable region. So these two observers exist a large non-observable region, and in this observer we use the 3D stereo space model, and we remove. In this observer, the non-observable region is very difficult to satisfy. So, if you want to make the observer converge fast, you can choose this part. But this observer contains a temperature expression. It's more complex than these two observers. And for this observer, because we use contraction property, and we can't guarantee we cannot control the convergence speed.
Are you sure about that you cannot control the convergence speed? Typically, I don't know this special case,
okay.
But when you have this kind of contraction property, the gain that the controller that you design or the observer that you design has a property that sometimes called infinite gain margin. So basically, it's always acting in the correct direction. So if you put the gain sufficiently high, you can, in some sense, control the convergence speed. But maybe this is not the case because this is switched.
Yeah.
So, I don't know. Are you sure that you cannot control? Have you tried like just pushing the gain very high to see what happens?
Yeah. Okay. I will consider this one later because I think that this is a problem for the whole process, and what we can guarantee is exponential project. So this will be considered easy.
Okay, thank you very much.
Thank you.
I'm done.
Okay, thank you very much, Samuel, for your questions.
Yep.
It's my turn. I would like to congratulate Nisu. I think you have done a huge work, going from modeling to the problems of identifiability, and finally finishing in observers, and it's a huge work. This is nice, very nice. Also, it's nice because you are trying to solve a real problem, using fundamentals of physics, chemistry, and control theory. And I think this is the way to advance. So you have proposed complicated models and complicated but useful models to develop these models for observers. This is very nice, and also it's very nice that the problem is motivated by a real application. So I congratulate to you and also to your supervisor, to Gina and Ramon Costa. I have some questions that are quite general, but I would like to emphasize. You move from when you are in the chapters 2, 3, and 4. When you are developing the models for the observer, it's very important to have good models. But you move from the 2D model to the 3D model and to the 2D model, and I couldn't see in the thesis, and also I couldn't see in the presentation what is the conclusion, which model is more adequate for the final. There are no a general model useful for all the possible utilities, but as you are using the models for observer, what is the conclusion about the models and the for the observer for the problems of estimation that you deal in chapter 5, 6, and 7? What is the best model?
Actually, in my thesis, I developed a 2D and 3D model, and as I say before, the 2D model is suitable for the case where the heat transfer between the tank and the external environment is not considered. So if you want to design a cooling system to control temperature, you should use 3D model. And in practice, the heat management with photofill and electrolyzer is very important. So in practice, we should use 3D model.
Does this conclusion appear in some part of the thesis? I couldn't find a conclusion about the models which is more useful for some part or for some the others. Does it appear in some part of the thesis?
Because the 3D model is very complex, and it's difficult to design observers directly. So first we consider a simple model. We didn't consider the temperature dynamics. Yeah.
Okay. I have a question which is related with the models about the parameters. The values of which appear in the tables that you have, for example, in table 2.1, 3.5, and 4.3, there are some parameters. For example, there are several, but we are going to fix one. The specific heat of metal hydride in table 2.1 appears to be 700. If you go to table 3.5, it appears to be 400. And if you go to table 4.3, it appears to be 5,400. So the values of the same parameter appears to be very. Go for example, go to table 4.3. 4.3. And we are going to find, just because we don't have too much time just to go to, so 4.3. I don't understand why there are so different values in the the specific heat of metal hydride is in that table 5,439, correct?
Yes.
Okay. Go to table 3.5.
3.5.
Yeah. 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 There you can see the value is 400. It changed for 5,000 to 400. Why?
Because when we analyze sensitivity for 2D model, we use the values from this reference paper, and in this paper the researcher give this value. However, the material used in this paper is different. It's different from the material it's different from the material of the tank we used.
But it seems to me that some parameters change the value when you use the 2D model and the 3D model. Is that correct? Go to the value. Go to the value of table 2.1. This is not of reference 1. Is of reference. To 1.
Yeah.
Yeah. The value there is 700. So it changed from 700 to 400 to 5,000. I couldn't understand why. But there are several parameters. There are several parameters which have the same, because you have written, I think you have done a very important work just to experiment, but I couldn't understand why the values, you have several tables in chapter 2, 3, and 4, and the values of several parameters change too much. I don't know why.
Because this value in the reference paper is the material is different with us. So if we want to analyze the sensitivity for in our case, we should use experimental value.
Yeah, but
as I said, the
sorry, Mingrui, but I understand. I understand that you show, I don't know in which slide, the experimental setup that you have been using only one experimental setup.
Yeah. I mean, the setup.
Yes, only one. Only, in my opinion, I don't know. It's just a question. In my opinion, if you are using only one setup, when you change the model,
yes,
in my opinion, the values of the parameters that you use in both models, in the simple model, in the 2D model, appear some parameters, and in the 3D model appear more parameters. That's clear. But the value of the parameters that are appearing in both models should have the same value. shouldn't
in my opinion, the sensitivity analysis and identifiability analysis is local. It's a local problem because it's based on the Taylor expansion. So I think if we change the setup and use another model, we should analyze sensitivity and identifiability based on complete thing.
Okay, thank you for the reply. I have also a question related with the observer. It's my last question. It also appears that the tables in that chapters in table 5.1 and table 4.3, there are some parameters which have different values, but that is not important by now. When you conclude about the observer, you have studied classical Lemberger estimation based on differential detectability, and also observer the high gain observer. When you conclude about these observers, it seems that the three work very well. If you can read it in the chapter, but for example, if you go to the conclusion of chapter 5, you can see the proposed estimation framework related with Lemberger is validated through simulation and experiments, demonstrating fast and accurate estimation of the state of the church. If you go to the chapter 6, it happens the same. The proposed method is successfully validated through simulation and works very well. What is the conclusion? What in your opinion, for this kind of systems, which kind of methods to estimate the state of the church is the best? What is your opinion about?
Actually, each appointment has its own advantages and disadvantages. As I said before, for lookalike observer, we should train the neural network it needs a large computation cost, but for observer, based on differential detectability, we needn't train the neural network. However, these two observers for 2D model have non-observable regions. So if you want to estimate the system trajectories more faster, I think the observer for 3D model is better, I think.
Okay. No, it's because you have studied 3 observers and you have an applied problem. There is no solution which is the best for all the application. But I was just trying to solve which is, in your opinion, the best for this application for metal elements. But finally, what is with of the contribution of your work, which is the most relevant, which is the contribution which makes you to feel more proud? What is the most interesting contribution?
I think okay. Here, actually, in my opinion, I think because the ancient model it's derived from different literatures, and different researchers already studied for example temperature dynamics and social reaction kinetics FRs. I think so. In my opinion, the observer design part is makes me more proud. I think.
Okay.
It's my main contribution.
Okay, that's perfect. Thank you very much, Mingrui. Maria and Samuel, do you have some additional question?
No,
No, thank you.
thanks.
Is there in the room or in the meeting some PhD who wants to ask Mingrui some question?
No, I don't have as a co-supervisor. Thank you, Carlos.
Okay. Fan Xuan, are you PhD? Do you want to ask some question? Is in the room someone who wants to?
Thank you, Carlos. I don't have any question.
Okay. I think we have finished. I would like to ask my apologies to Mingrui and to the supervisor for not being there. You deserve, Mingrui, to be there, but I couldn't. I am very, very sorry because I couldn't be there. So my apologies to you and also to your supervisor. If you don't have, if any PhD have any additional question, we finish this act, and the jury will meet now just to discuss about the qualification. Congratulations to you and also to your supervisor.
Thank you, brother.